Welcome to the virtual course number 7 promoted by the HERACLES project. The virtual course number 7 will be dedicated to technologies for material characterization via laboratory studies and portable instrumentation. The instructors of this course are João Pedro Veiga from Uninova, Antonella Curulli from CNR, and Paris Poli from FORTH. So the virtual course number 7 is organized in 3 parts. The first part is dedicated to an overview. The second part is dedicated to the ex situ analysis using laboratory infrastructures. And part number 3 will be dedicated to in situ analysis using portable instrumentation. We will now start part 1 of this course, overview. So the in-depth knowledge of material properties and the weathering behavior is an important basis for developing and planning effective and cost-effective preservation actions. The well-accepted systematic approach to a sustainable cultural heritage asset material preservation can be organized into 3 important phases: the anamnesis, the diagnosis, and the therapy. Usually, the overall aim of diagnosis is the analysis, the quantification, the interpretation and assessment of material deterioration, the damage rate, considerations on the weathering factors, weathering processes, and weathering characteristics, as well as the material type, the monument asset characteristics, and the time factor. And in this course, we will be dealing mainly with the diagnosis of these materials. A complete and accurate diagnosis, together with a correct anamnesis, are the basis of therapeutic and preventive preservation measurements, such as cleaning, desalinization, surface protection, materials repair and replacement, shelter relocation, etc. So the diagnosis approach, which combines in situ and ex situ laboratory analysis, is focused on different scales of the deterioration. Particularly, the in situ analyses are applied to obtain information on visible deterioration at the mesoscale and at the microscale, while the laboratory ex situ analysis is more dedicated to provide information at the microscale and at the nanoscale, using different types of equipment. So a detailed knowledge of the materials that constitute the cultural heritage assets and their degradation mechanism is required. To achieve this objective, the proposed methodological approach should be the following. So first, we do an evaluation of the analytical strategies in terms of techniques to apply to the different cultural heritage assets and definition of the analytical protocol. The in situ investigation through not or minimally invasive in situ techniques, and then an ex situ study in laboratory to better characterize the structural, chemical, and physical properties of the materials. So the ex situ analysis will be focused on the identification of materials and determination of their alteration and deformation mechanisms by using high resolution sophisticated measurements. For many cultural heritage materials, the characterization begins with macroscopic observations and measurements by the in situ investigation. The next step for many materials is the microscopic examination using the ex situ analysis. So the selection of the ex situ analytical method or technique is dependent on type and value of the sample, the sample matrix, the precision and sensitivity of the instrumental measurements technique, and the availability. All phases prior to the analytical steps are important, including sampling, which has to be carefully planned and representative. Sampling is indeed a very important procedure and often constrains the analytical stage. So it should be accurately described and samples have to be stored properly. Sample preparation can vary depending on the test to be performed and on the characteristics of the material itself. So the diagnosis and analytical method, an ideal method for analyzing material of artistic or historic or archaeological nature, should be, as we know, non-destructive, that is, respecting the physical integrity of the material or object, should be fast, so that large number of similar objects may be analyzed, or a single object can be investigated at various positions on its surface. It should be universal, so that by means of a single instrument, many materials and objects of various shapes and dimensions may be analyzed with minimal sample treatment. It should be versatile, allowing with the same technique average compositional information to be obtained, but also local information of small areas from heterogeneous materials. And it should be sensitive, so that object grouping and other types of provenance analysis can be done not only by means of major elements, but also by means of trace elements and fingerprinting. And finally, it should be multi-elemental, so that in a single measurement, information on many elements is obtained simultaneously, and more importantly, information on elements which were not initially thought to be relevant for the investigation purposes are gathered. So the in situ diagnostic studies provide important quantitative information on materials and on their weathering state. They enable the examination of the materials in their actual condition without any changes due to sampling or removal. Many different investigation methods and instrumentations have to be developed. The mode of operations ranges from non-destructive to slightly destructive, for instance. Most of them allow only spot measurements and provide information for very limited areas of the cultural assets. Therefore, selection of the most critical and interesting areas of the monument and a sufficient number are required in order of a reliable and representative result. The portable instrumentation for in situ materials analysis used at the HERACLES consortium consists of a group of techniques that we can take to the monument itself. And in these areas, we have, for instance, the portable laser-induced breakdown spectroscopy, which is laser-based technique and provides information on the elemental composition of the area under analysis. It is a fast technique and has no particular sampling requirement, and it is suitable for fast screening of materials. Also, the portable multispectral imaging system, which is an imaging technique that combines digital imaging with spectroscopic analysis and may remotely and non-invasively give spatial and spectral information about an object or a monument. Also, portable Raman spectroscopy, which is a non-destructive laser-based technique that probes vibrational, rotational, and other low-frequency modes in molecules and materials. The portable Raman system can be used to determine the nature and composition of a number of weathering formations in different areas of the monuments, such as pollution, crusts, biodegradation, and salts efflorescences. Another technique is the 4D surface volume topography, which is a non-invasive, non-destructive, portable, and low-cost technique to measure the topology of a surface and its variations over the time. And finally, the drilling resistant measuring system, by using the drilling resistance measuring system that have two distinct aims: the evaluations of the current state of preservation of the stone and the sampling of the drilling residue dust from distinctive interval depth for further physical-chemical analysis in the laboratory. This portable instrumentation for in situ materials analysis will be the object of study of the part 3 of this virtual course number 7. While referring to ex situ investigation, the laboratory materials characterization is performed by a multitude of different analytical procedures and allows to assess different properties such as composition, microtexture, porosity, and so on. Therefore, it is crucial to select the appropriate method or combination of methods which ensure the most effective approach to document the materials degradation issues. In the frame of an accurate diagnosis, samples of an unweathered, that is, original materials, weathered, and eventually treated samples are necessary for laboratory analysis in order to characterize and classify the original material, characterize, quantify, and rate the material degradation due to weathering, identify and quantify the weathering products, and characterize and evaluate the remediation and preservation treatment. In this context, sampling of the weathered and treated materials at the cultural heritage monuments must be performed carefully to minimize any additional damage. Number and quantity of samples have to ensure that the defined scientific and practical problems can be approached systematically. Furthermore, many analytical techniques need only a small amount of material, while in several cases, reuse and recuperation of samples is possible. Finally, based on the results obtained from the in situ investigations, sampling can be selective and limited to only a minimum level, depending on the individual case. Precise documentation of sample is also required. So for the material composition study, several techniques can be used. For instance, spectrophotometry, which is considered as a technique for molecular characterization. It is widely used as an analytical tool for non-invasive analysis of cultural materials, including pigments, paint binders, or paintings on panels, parchments, and walls, as well as on canvas and plastics. This technique is considered non-destructive and the sample recuperation is full. Also, Fourier transform infrared spectroscopy, which is useful ex situ technique in a sense that it supplements the material characterization by studying the vibrational modes of chemical groups present in the sample. It is extremely useful in characterizing organic materials used for stone or material consolidation. The small amount of sample and its high spatial resolution allows the identification of micrometric mixtures of compounds which constitute the samples, the determination of minor trace compounds resulting from weathering and degradation phenomena, as well as the characterization of existing restoration works. This technique is considered non-destructive and the sample recuperation is full. X-ray photoelectron spectroscopy is another technique, which is a multi-elemental and non-destructive analytical tool providing chemical state information of the detected compounds and elements. It probes surfaces, but it can give bulk information by analyzing the cross-sections or pulverizing the sample. This technique has been widely used to analyze archaeological and artistic materials, generally in the characterization of coatings or patinas. In fact, considering the material degradation due to pollution, the transformation of the outermost atomic layers of a stone material induced from absorption and deposition of air pollutants and particulate matter can be detected by means of X-ray photoelectron spectroscopy. Consequently, it is effective for characterizing patinas, incrustations, efflorescences, and related phenomena. As a surface analysis technique, it is crucial in the evaluation of remediation treatment of the surface. For this technique, the sample recuperation is possible. Also, in the study of the material's composition, the laser-induced breakdown spectroscopy can be applied both in laboratory and in situ environments, and gives qualitative and semi-quantitative analysis without prior or special preparation of the sample. It is a high-resolution analytical technique, since sampling is performed upon irradiation of the material with a strongly focused laser beam forming a spot of approximately 200 micrometers in diameter and has 20 to 30 micrometers penetration depth. Almost 0.1 micrograms of mass removed per laser pulse. Another very important advantage of the technique is that it enables stratigraphic analysis of the samples in the range of a few micrometers, and thus it gives depth profiling, but the sample recuperation is not possible. LIBS provides analytical information for the determination of minerals, as well as for discrimination of building materials, such as sandstone, limestone, and marble, and for the composition and classification of historic patinas on buildings. Usually, LIBS can be used together with micro-Raman analysis for the detailed characterization of different overlayers present on the monuments, as for example, black crusts from pollution, salts, efflorescences, and so on. X-ray fluorescence is a powerful characterization technique for the study of cultural heritage materials. It provides non-destructive elemental chemical composition of a sample already collected, needing almost no sample preparation for qualitative or semi-quantitative results. For the study of mortars and materials collected in built monuments, the information on elemental composition helps the interpretation of results provided by techniques that are devoted to identify the mineralogical composition, such as X-ray diffraction, Raman, and FTIR. The X-ray fluorescence technique is considered non-destructive, since the sample recuperation is full. X-ray diffraction is one of the most useful ex situ characterization techniques, and together with X-ray fluorescence is considered a basic analysis tool for the characterization of materials. Although XRD is not a destructive technique in itself, it also requires sampling. However, it can give definitive information on the crystalline phases present in the sample, qualitatively and quantitatively. Moreover, it is fundamental for the identification of mineralogical phases in inorganic materials. These two techniques, X-ray fluorescence and X-ray diffraction, will be the object of part 2 of this course. Still in materials composition, in the material structure and texture, we have the micro-Raman technique, which is a spectrometry technique that can be used in any application where non-destructive and microscopic chemical analysis or imaging is required. It allows to rapidly characterize the chemical composition and structure of a sample, and almost no sample preparation is required, reducing the potential danger for cultural heritage artifacts. Micro-Raman microscopy allows to obtain information about inert inclusions, neoformed crystals and aggregates, microcrystalline structures, being useful for the non-destructive characterization of inorganic materials such as mortars, binders, and stones. It might be useful to supplement or confirm results obtained with other methods. This technique is considered non-destructive, and the sample recuperation is full. For the material structure and texture, we have the confocal laser scanning microscopy that can generate accurate three-dimensional images revealing detailed information regarding structures characterization. This technique is well suited for the cultural heritage materials since it is non-destructive and non-invasive, while allowing surface topography of samples. In the case of weathered samples from built heritage, it allows high spatial resolution 3D imaging in very small specimen areas, which is useful for the detection of biodegradation phenomena, like the presence of algae, cyanobacteria, lichens, and fungi. The sample recuperation is full. Scanning electron microscopy gives valuable information regarding the morphology and microstructure of the sample under test. These data, mostly qualitative, are extremely useful because they document the current morphological status of the object under study, but they can also drive and guide consolidation procedures. The energy dispersive spectrometry gives chemical element information complementary to other techniques such as X-ray diffraction, X-ray fluorescence, and X-ray photoelectron spectroscopy, with the advantage of results are on the observed spot. Although in the literature this technique is considered non-destructive, the sample recuperation is not compatible with other techniques. The petrographic microscopy represents an important tool for a detailed analysis of minerals by optical mineralogy in thin section, since the microtexture and structure are critical to understanding the origin of the rock or stone under study. The mineral content and the textural appearance can be evaluated. This technique is complementary with X-ray fluorescence and LIBS. Individual mineral grains from a rock sample may also be analyzed by XRD when optical means are insufficient. The technique is destructive, as most mineralogical cultural heritage samples have to be sacrificed. Atomic force microscopy is mainly used in surface characterization and can be useful in the studies of aging, conservation, and cleaning effects on material surface for the assessment of behavior of coatings and protective layers, and measurement of the size of aggregates. The sample recuperation is possible. Nonlinear microscopy uses tightly focused femtosecond laser pulses to perform high-resolution microscopic measurements. With nonlinear imaging is a type of laser scanning microscopy. Its potential for depth-resolved imaging to study a number of materials of interest in cultural heritage has already been demonstrated. In fact, nonlinear microscopy has been used for characterizing different materials such as varnishes and parchments, for determining the presence, the thickness, and aging of linen glues in paintings, and the corrosion layers in metallic objects, as well as for studying paint layers. For the surface volume topography, using a laboratory instrument, relies on spectral and scanning white light interferometry and is devoted to measure the topology of the surface and its variation over time. When studying physical properties, thermogravimetry, differential thermal analysis, and differential scanning colorimetry are also possible to be used. TG-DTA offers characterization data of the investigated samples regarding its behavior under thermal stress. It studies mass loss of the sample when the temperature is increased. Usually, volatile molecules such as water are released. Although it can reach temperatures up to several hundred degrees Celsius, the useful range is much lower. The SE application to binder mortars give information on the thermal power heat-producing rate produced by the hydration reactions. The timing and shape of the heat flow curve obtained by colorimetry is an indicator of relative performance of binders, mortars, and of potential adverse interactions between materials used in the mixture. Unfortunately, the sample recuperation in these cases is not possible. Finally, spectroscopic ellipsometry provides accurate measurements of materials, optical and structural properties of a broad range of materials, and allows the determination of surface chemistry features. Spectroscopic ellipsometry aids the optical characterization of surface modifications. In this case, the sample recuperation is full. So this concludes the overview, part 1 of the virtual course number 7.